Quick warning up front, these open-style desktop engravers are not safe to use. They skip all safety features to be able to offer them for a low price. My precautions are off camera, so please don't recreate what you see. Bwah. Hey guys, in the past we looked at a cute, compact, cost-effective, Q-switched fiber laser engraver from Commarker, which they called B4. Soon after we got this monstrous mighty Mopa machine. This is still my daily driver and there's not much it can't do. They called this model the B4. Now you wouldn't believe what just arrived. It's an altogether different beast called B4. No, actually this has been sitting here for quite a while, and the manufacturer has since reworked their naming scheme. What we are looking at today is an early version of Commarker Omni 1. Omni being a prophecy of what this guy can do supposedly. This is a pulsed UV laser, 355 nanometer. Less than 25 nanosecond pulse widths seem to be possible if I read that right. Shorter being better in this case, because, well, squeezing that 5 watt average power into ultra short impulses makes them all the more potent. Gotta say though, those numbers on their own don't exactly blow me away. My favorite infrared daily driver is 60 watts nominally, and it can do pulse widths down to 2 nanoseconds. What gives? Why is this weakling in the same price range? Well, here's a little preview from the future. But let's ease into this. There might still be some normal arts and crafts people watching who might want to use this for, I don't even know what they do, engrave their iPhones and sunglasses or whatever. Nerdy stuff coming at the end. This machine is built with higher quality components than all the previous ones. A real chunky, heavy galvo head and a massively oversized Z-axis. We will take advantage of its near-perfect verticality in a moment. And since it took me so long to film this, the latest version that Commarker sells right now is nicer still, all black everything, some bug fixes and a motorized Z-axis. Assembly and initial setup can be done in 15 minutes or so. All required tools are included, and there is even a USB stick, prepared with the basic control software and a rough correction file, to compensate for manufacturing tolerances in the galvo head and give you reasonable accuracy right out of the box. Furthermore, you get a foot switch, some guide rails, economy class safety goggles, and nowadays apparently a lap jack and a fluorescent preview helper. I'm getting kinda jelly over here. Indeed, these UV sources don't seem to have a built-in red pointer to indicate where and in what shape you're about to wreak havoc. It does offer some weak standby simmer though. That helps, but it's only visible on something fluorescent, so this thing is a good idea. I also appreciate this bonus grounding cable from a supplier with a memorable name. At first I thought it was either a YouTuber privilege or a mistake that I got 2 f-theta lenses. But no, it seems like they include 2 with every one of these machines. It seems to be one for a 70 by 70 millimeter working area, and a big flared out one for a 150 by 150 millimeter working area, and a much longer focal length. Cool, thanks, I guess. But why should I ever switch and not just use the big one for everything? Well, for most day-to-day tasks, this large lens will in fact be perfectly fine. But the formula for focal spot diameter, besides fixed values like pre-lens beam diameter, wavelength and beam quality, also has a variable for the lens's focal length, meaning that the 70mm lens should give us a smaller focal point. 33.9 micrometer according to theory, and 1.9 micrometer according to Commarker's marketing. What? Congratulations, now you've made me curious. I tried a few different focus settings for each lens because the beam is hourglass shaped. So a wrong setting there could degrade our spot size. It may be tempting, but don't torque these to 355 Newton meters, no matter what the label says, trust me. To quickly, roughly home in on the focal length of a new lens, we can just listen closely while cranking the Z-axis. The loudest pew-pewing will be reasonably close. It's not enough though. The shallow depth of field, especially of the smallest lens, makes it really difficult to dial in exactly the right Z height. And I'm saying that with a good microscope at my side, not sure what I would have done without that. Here, from left to right is a calibration slide, some eggs, the best spot size I was able to get out of the large lens, and the best spot size of the small lens. With the large lens I got down to 53 micrometer diameter spot size. The small lens grudgingly gave me 40 micrometers after many attempts and a lot of fine-tuning. That's only 20 times as much as what the manufacturer advertises with. With their 60 watt MOPA fiber laser and a 110mm field lens, I get between 50 and 60 if I try hard. The eggs or even peanuts were the most interesting observation to me. When the source left the factory, it was tested for and certified as a beautiful round, almost TEM00 emitter. The problem here was that I got a little bit too creative with the impulse timing parameters, which seem to have a huge impact on beam quality. I will open the laser source later and then we can try to find out why. For now it just matters that 30 kHz 12 nanoseconds seems to be the sweet spot for the sweetest, roundest spots. I guess what you could do for perfecting focus if no microscope is available, just fill some small test shapes with lines, spaced exactly at your expected line width. Then some dollar store smartphone clip-on magnifier or some AliExpress magnifying spectacles might be enough to tell if there's overlaps or leftovers. That certainly seems easier than trying to measure point diameters. To do it efficiently and reliably, it needs something smarter though, an encoder for the Z-axis or a rangefinder or something. Now nobody can say get to the point, but I will. An infrared MOPA machine is hard to beat in terms of versatility. In my video about it I've shown color marking, deep engraving, welding, cutting and more. A few rare materials are surprisingly resistant to infrared though. Precious metals and copper for instance have fantastic reflectivity to infrared, making any attacks inefficient, so you really have to overwhelm them with maximum power. Plastics can be troublesome too. They can melt in the focal spot and fuse back together behind it, or char, or show unwanted discoloration under less than perfect settings. Materials that are transparent to our visual wavelengths tend to be transparent to 1064 nanometer as well, so stuff like acrylic and glass is nearly immune to MOPA fiber lasers. Additionally, germanium, silicon, and gallium arsenide can literally be used as lenses and windows for the near-infrared range, so those are tricky too. And high carbon content materials like wood, food, and terrestrial life forms tend to char easily, and then their carbon becomes immensely heat resistant. I didn't test all of those examples myself. Nothing is immune to a pulsed, focused 355 nanometer UV laser like this. There probably are some exotic, high-purity, wide bandgap, special-purpose crystals that are, but nothing you'll meet out on the streets. Plastics of any color, not a problem. Dyed samples can be selectively bleached, and white ones can be ablated, cut or charred, for a nice, crispy, contrasty marking that is durable too. Same goes for a nice, bright, cheap wood that was so surprisingly IR resistant in the past. Or any other wood. Focusing directly on the surface results in a cool ablation, with very little burning and therefore no color contrast. So this is slightly defocused and slowed down to do something. The aforementioned cool ablation in combination with the incredibly small spot size unlocks something pretty amazing with wood. After less than 10 passes we've made a cut through this material. It's not a huge accomplishment to cut through this weak, thin plywood, but doing so with a sub-millimeter cut width and hardly any charring, I found this quite impressive, mon ami. Clothing, fabrics, all textile materials can be altered as well. Imagine offering near-instant customizable merch. My results on dyed black, pure cotton were not very durable, but I didn't try very hard to figure this out, to be honest. It seems like cotton fibers are easily damaged and then they just crumble away, revealing a fresh, black, unharmed layer underneath. If there is a small synthetic fiber content, it's very easy to get the parameters right, and walk away with a long-lasting visual effect and no damage to the material's integrity. Just like last time, I'll share all my Lightburn projects below if anybody needs a starting point for material parameters and tasteful drip. Commarker calls this machine 16K HD and then refuses to elaborate further. I believe the Galvo position programming resolution is a 16-bit number for each axis, so minus 32,000 to plus 32,000. That's actually a much finer resolution than 16K, even if a few bits are subtracted due to noise and nonlinearity. But what we are actually limited by is the spot size diameter per lens area. And that's roughly 650 dpi with a smaller lens, so about 1,800 meaningful points per axis. That's halfway between Full HD and 4K, so excellent. The best I have, but not 16K. Sunglasses and iPhones? Sure. We'll leave a mark one way or the other. Sunglasses and Commarker's complementary goggles. Both should be UV absorbent. They evidently are, but they wouldn't even have to do anything special for that. This laser will happily chew into cheap soda lime and fancy quartz glass alike. Modern, hardened smartphone and watch glass types are a special challenge. They are submerged in a molten salt bath. That creates tension in the material, similar to the ever-popular Prince Rupert's drop. This makes it strong, but as soon as there's a teeny tiny little chip, it will inevitably propagate as the compressive stresses see their once-in-a-lifetime opportunity for freedom and equality. Oops. So we can do this material, it just won't be good. I wouldn't even recommend working on the sideways metallic antenna elements, not without further research. Those can have crucial geometric features, disturbance of which could cause problems with reception. It goes without saying, we could do those too. If this juicy, thermally invincible copper chunk isn't immune, no metal is. So yeah, superficial engraving of all materials. That is what Commarker Omni is good at and meant for. Some say you can't really make deep cuts with this one. They have a point, but I would phrase it differently. The superficial ablation I've shown so far is nothing other than material removal. The energy of a photon is inversely proportional to its wavelength. So even though this one has a lower average watt number compared to my infrared machines, it is similarly or more effective. The primary mode of operation of an infrared laser is photothermal ablation. It tries to melt or evaporate or decompose little chunks, and hopes that they explode away due to rapid thermal expansion. 355 nanometers are a lot less heavy-handed than that. On organics and polymers, UV can sever chemical bonds directly, without necessarily superheating anything. I'm sure my fellow laser enthusiasts are all familiar with the world-famous Trumpf matchstick photo. We are getting there. Because we don't depend on destruction by means of heat as our method of marking stuff, we can work on coatings that serve a purpose and need to remain intact. Say, painted car parts could be tastefully decorated, without exposing underlying steel and inviting rust. Metal removal, I suspect, has to be photothermal no matter which wavelength. But here too does UV have an advantage. It is absorbed much more readily by most victims. When working on glass, I believe we get to witness multi-photon absorption, and possibly even some plasma formation. That's why we see this bright white light throughout the process. How did I get here? Oh yeah. Nothing inherently keeps UV from making deep cuts, quite the contrary. But it's certainly very slow in practice. I believe that's due to the absence of little superheated explosions at every impulse. Those help infrared machines expel waste material and keep the working area clean for the next pass. Additionally, we've got this shallow depth of field that does most of the work at waist height. If we just go straight down, we will get a narrow, shallow hole. But at some point you can kinda see that the cone above that feeds the waste gets mostly cut off by the edges of our hole, and there is not enough intensity in that wide part of the cone to chip away at those corners and make its entrance wider itself. So we kinda just get stuck at some depth unless we prepare ourselves a conical entrance. A wobble setting in Lightburn helps by making all of these shapes wider, but only so much. There is a non-negotiable aspect ratio limit set by our focal lengths. And I'm not convinced that wobble is the best option anyway. It's like drawing with a thick Sharpie. You're certainly losing details. Instead, I prefer to duplicate a shape and offset that by the planned depth of cut. And then I just fill the resulting perimeter. Actually, I prefer not to pulverize glass at all, because this is a huge health hazard. My air quality particle thingy picked this up on the other side of the room, so as cool as it is, never ever without appropriate dust extraction. Here's a cute side effect of this stuff only happens in the focal spot situation. Don't blink or you'll miss it. Okay, here's another chance, but a bit higher up. Okay, there will be many more chances in a moment. Because this is so cool, you can embed markings at any height into glass. Imagine the possibilities for diffractive microstructures and fiber brack gratings. Or you could just paste some AI slop onto cheap merch if you want to be that kind of guy. It's probably very lucrative to be that kind of guy. A good old CO2 laser, a much cheaper and higher watt machine, can also mark glass through thermal shock and microfracturing. I guess that's suitable for a thick-walled beer mug, but even in that case I would flinch every time it sees a significant temperature change. With UV, much more delicate work is possible, and there is absolutely no degradation of the surrounding material. Does anybody know what a microfluidic device is? Yeah, me neither, but I can now make them from dirt cheap microscope glass slides in 10 minutes or so. They might even look good with proper plumbing. Unfortunately, I just have a pipette shoved into the hole, so it'll be a while until this becomes a dye laser. Back to the comfort zone. Will it PCB? Absolutely, better than any other laser engraver I've ever tried. Here's a footprint that Texas Instruments calls YBG. It's a bare silicon die with balls on it, basically. If this wasn't the best temperature sensor in the game, I wouldn't want to deal with it, but here we are. If we make matters worse by trying to sneak a 0.2mm trace between two balls, then we get generous 80 micrometer clearances. That's a little more than 3 mil, or 2 minimal spot size diameters. So pretty challenging to etch chemically, not really doable with a simple at-home setup. Due to isotropic under-etching, I'm pretty sure. But no problem for Commarker Omni 1. And I'm not just talking about the ridiculously small feature sizes. My other machines will also gladly remove the copper layer, and faster too. But if they get as much as a glimpse of the FR4 substrate underneath, they'll burn it, carbonize it, make it slightly conductive, deform it and the surroundings, and delaminate and deep fry thin traces too. Supposedly there are settings to make this work with a MOPA as well, but it needs attention, time-consuming fine-tuning, and a substrate with a superb flatness. With this one it's completely chill. A few passes into the substrate, no problem. It just cleans it up. And how about a microscopic isolation slot, an end mill for which doesn't even exist as far as I'm aware. This operation is a little burny because I'm spending so much time in one place. That could be fixed by adding pauses in between passes. Due to the nasty, hazardous fine dust that this creates, I will very gladly continue to outsource this kind of thing. But you know, in a pinch, if you need something in an hour and not in a few days, this could really save your day. Here's the devilish part itself, TMP 119, if you know you know. And a lovely PCB-way flexible circuit board for it. And here's what our UV Commarker made for us. It could have taken a few more passes. Both the no copper zone and the insane isolation slot. And we could have covered the whole thing in solder mask before engraving, and then selectively just open up some pads. But I hope as a demo piece this shows why I'm absolutely in love with this laser. One more round, just to make this clear. This thing is a one-click single-layer PCB manufacturer. The very thing I've been dreaming about before I got acquainted to PCB-way. It drills holes, removes solder mask from pads, etches a copper layer, and then it also cuts out the whole board. A prototyping laser machine for this purpose made in Germany costs 70 to 200,000 euros. It's got a nice enclosure and dust management, to be fair. What about silicon? I volunteered to help a battery researcher friend turn a large wafer into as many small wafers as possible, and that worked very well. I took this one outside thinking about the silicosis risk, but on closer inspection, the silicon oxide, the glass I did before, is what's actually bad and carcinogenic to inhale. Ultra pure silicon like this, not so much. So we might as well get a living room MEMS factory started. What do you think? I briefly tried to sneak up on some packaged silicon too. The idea here was to find out which impulse settings would just barely not damage a die. 40 kHz, 15 nanoseconds. 16, 17, 18, 19, 20. That looks usable, just some slight discoloration. 40 kHz, 20 nanoseconds with this 5-watt source. The same settings will slowly photochemically ablate an epoxy molding, but I think we can safely go full throttle at least until the first few bond wires start peeking out. This is an application-specific integrated circuit, made for reading the time projection chambers in the star detector around a heavy ion collider at Brookhaven National Laboratory. If you need a better explanation than that, you've got to ask my friend Gigabecquerel, who has donated this exclusive souvenir for decapping. Yes, there seems to be a small range of settings where we preferentially hurt the epoxy package, leaving the bond wires and die intact. But these settings are so gentle that there's hardly any material removal. The crumbs just stay there, so I think this would work much better with extreme air assist. I finished this part chemically because I didn't want that kind of dust spread out to every surface in my lab. I'm optimistic, but I can't say for sure that there is a UV advantage here. I mean, with infrared you can also go almost all the way and then finish the last little bit chemically. This large area is most likely bucket brigade analog delay lines for time-to-digital conversion. The last stunt of the day is experimental to say the least. Then again, machines that are meant for this are vastly more expensive, so maybe it's worth investigating. I'm talking about suspending 3D models in glass blocks. Hardware-wise, there's not much to it. The Z-axis is very good and vertical already. I just added a closed-loop stepper motor to it, whose encoder is observed by a Raspberry Pi Pico, which commands steps in the right direction to keep it at a destination position. That in turn can be remote controlled over a WebSocket, and that's all the hardware needed to pull this off. I think the newer Commarker Omnis have a stepper driver built in by default, and a motorized Z-axis, so with those it would be even easier. But the software is a bit of a struggle, not gonna lie. All of these Galvo laser engraver machines use a BJ-JCZ controller card. The language in which that expects to be programmed in is not published. Or so I thought, until I found Balor, an open source command line interface for these, with most of the control words successfully reverse engineered. I would have used Lightburn for this, but they keep postponing their automation support, in favor of other changes such as discontinuing Linux support. Balor looks much friendlier with its Python script file extensions, but don't be fooled. It's pretty hardcore. You can feed it ngC G-codes, images for rastering, SVG vector files, and texts through dedicated preprocessors each. And then their standard output can be piped to the sender, which negotiates with the machine. Have you ever wanted to see what kind of Python code would come out of a brain that has been wired for C? Well, definitely have a look at this project. I had to Wireshark some USB packages to find some control words that had not yet been figured out and understood. I think they are related to pulse width and frequency, but only in some lasers. And then I actually had to find a model that was worthy of being perpetuated in a glass cube, and to become the highlight at the end of my video. We do have a whole new dimension to play with here, transparency. That's not something that freely available 3D models care about. They are just a surface with no holes ideally. I guess a human body with the skeleton and nervous system would go hard. But I don't like humans. I want something profound, inspiring, something eternal. Then I had to make another thing that's basically a resin printer slicer. It detects intersections of STL model polygons with horizontal slices. If it finds one, it just draws a short SVG path. That works, but when I say short SVG path, depending on the model's resolution, it can really be an atomic engraving process afterwards. And the segments are not ordered geographically, so we always need a jump delay between points to let the mirrors settle down. A jump delay that would ideally depend on the speed that they just reached before, to save some time, so this can get quite complicated if you want to do it well. It's cool to watch in a time-lapse, but it's agonizingly slow in reality. I used all the waiting time to try and sort the segments geographically. That ended up putting too much heat into too small of a volume of glass, cracking my test piece. I'm not too upset about that, because we are making progress, and it gave me this crazy cool footage. I should have taken the hint and seen right through the next issue when the focal length was not what I was expecting it to be. We should be leaving a mark about 5 mm above ground in this cube here. But no, we are barely scratching the aluminium piece below. But I just made a height adjustment and let her rip normally. Wasting a €10 glass cube. Do you get it? It's not surprising in hindsight, but I really didn't see this coming. We are entering a material with a very different refractive index. It's like we are trying to grab something underwater based on observation through air. If we don't compensate the height settings for that, we miss our marks or accidentally create a portrait of your mom. The next version came out with better proportions, but all fuzzy. Turns out the impulse timing parameters for the smallest spot size in X and Y don't automatically lead to the lowest affected volume in a glass cube. With those we are almost getting little lightning strikes in the depth of field. Vertical streaks, taller than my intended slice height. A few good old parameter test grids reveal better settings than that. 38 kHz 12 nanoseconds seem to lead to the thinnest marks in this glass composition on my machine. Probably slightly different for everybody. With focal length compensated and impulse timing fine-tuned, we are getting an absolutely exquisite model. But transparency doesn't suit El Risitas any more than it did before. Who would have thought? I think something technical like an engine would be much better, or a spacecraft, real or fictional, or a 3D fractal rendering, or the Hollow Earth conspiracy illustrated, or an ancient monk skeleton embedded in a statue, or the anatomy of the assumed spherical cow, or Midra, Lord of Frenzied Flame, directly converted out of game assets. I don't know, I can't decide. There are too many options. But I'm pretty sure that if something can be drawn in Blender, we will find a way to turn voxel transparency into laser point density. But that sounds like another video. Since it is Teardown o'clock already, I thought I'd beam down a wholesome buddy to keep Risitas company, with solid infill this time. It kinda works, but it's getting discolored and too hot again. Also, there is an almost 3D printeresque interaction between subsequent layers. If one is opaque, it's much easier to deposit another one above it. A hole causes sagging because there's nothing in the way of the laser beam. So we kinda almost need bridge and overhang detection and slow down in those cases. Anyway, long story short, pretty cool. In the basement, where there's usually the fiber laser source, we got not that much this time around. A stepper driver, I had no idea. I thought this was only in the newer, up-to-date models. A 12 volt, 5 volt and plus-minus 15 volt switching power supply. And an authentic Beijing JCZ controller card. For the fast, time-critical mirror motion control and some GPIO pins. Construction quality here seems acceptable for the price of one of these machines. They are making an effort with some cable shoes, labels, and crimped ferrules. But there are also some instances of just stripped cables raw-dogging the screw terminals. I'm sure this is just an early model and their new black machines are going to be nicer. Goodbye. Upstairs is where the real magic happens, and I'm not just saying that. The whole laser source uses a single skived heatsink as a baseplate, with no less than 7 DC fans roaring through. This 5-watt machine is pretty loud in operation. The 10-watt version comes with a water cooler. That should be a lot more tolerable. There seem to be some heat pipe or even vapor chamber inlays in the baseplate. That's pretty sick. Up here on the top floor we've got a large thermoelectric temperature controller for the pump diode. 2 smaller controllers for the crystals in the optical cavity are on a kind of main board in the rear. Love the chunks weight type capacitors. I read vent at first glance, which might be a label on other caps. What a funny coincidence, huh? This source is literally just controlled with 2 pins and ground. Gate seems to be a high enable signal, without which only a weak preview point comes out of the source. The pulse pin gets a square wave, frequency of which sets the laser output frequency, 30 kHz for me most of the time. The high-level pulse width programs the laser pulse width, but nanosecond stuff is pretty hard to deal with, so there seems to be a ×1000 scaling factor, meaning that a 24 microsecond pulse width on the pulse pin leads to a 24 nanosecond laser pulse width. A very, very friendly hackable interface, in case anybody ever wants to point this into a microscope, or make an autofocus rangefinder kind of thing based on time of flight. In the bottom left corner we've got a Q-switch driver, looking very similar to this one, except a little less water damage. This is an RF source that will tickle a crystal in the optical cavity at its favorite frequency, making it more or less transparent. It could be visualized like an electronically actuated shutter, just without moving parts, so that things can happen on a nanosecond scale. Right next to it, on the other side, lives an 808 nanometer continuous wave fiber-coupled pump diode. A fab, if you will, on a copper heat spreader on another thermoelectric cooler. This little guy is the sole source of optical power in this whole system. It has to deliver over 5 watt of infrared through the yellow fiber optical cable, so that even after the lossy wavelength conversions more than 5 watt are left. This is a wear item with a lifespan of many thousands of hours usually, but I love that it's accessible and easily replaceable outside of the cavity if need be. And now I'm afraid we have nowhere else to go. Oops. I've briefly glimpsed the rubber seal and humidity absorbers, so I will prepare everything for the shortest, cleanest visit possible. So system all warmed up and software prepared to launch a quick engraving program. That way I hope we can witness this miracle and get back out without inconveniencing anybody. Sorry to disappoint, but I don't think I can explain this thing all the way. At least not without saying, this happens because this magic crystal works that way, at every corner, but I'll do my best. A couple of watts of 808 nanometer near infrared are coming in from 10 o'clock, with some divergence possibly after exiting the SMA connector. So the first part I believe is a collimation package. Then comes a pretty standard DPSS arrangement. I think what we are pumping here is a neodymium doped yttrium aluminium garnet, not an orthovanadate which we've seen in coherent verdi. That crystal would have a better absorption cross-section. Had they used that here at this power level, they could have gone with a much shorter crystal. One could visualize this as an energy accumulator. We are exciting the neodymium ions for a while, and then we let them all at once crash back down to their resting state in a chain reaction. Using the acousto-optic modulator, the aforementioned electronically actuated nanosecond shutter, all the stored energy is re-emitted as 1064 nanometer light, and after passing through a pinhole it encounters a real mystery. If I'm not mistaken, this dichroic mirror does so much heavy lifting in this system, almost literally RGB sorting, which is what dichroic devices do. Different wavelengths go towards different angles, but man have they given this thing some extreme arbitrary angles, if I'm reading this right. Since different wavelengths go to different directions, another small hole downstream can be used to strip unwanted harmonics and maybe even modes. Only 1064 nanometer is supposed to go to the second harmonic generation crystal. I think this is going to be a KTP, which has a worse conversion efficiency, but it doesn't have to be heated to 150 Celsius to be happy, and it's more robust than LBO. Either way, 2 photon absorptions happen in that crystal, turning 1064 nanometer photons into 532 nanometer green light. A less than optimal conversion efficiency is not unwanted here, because the next guy, which could be a barium borate, happens to have the ability to absorb unconverted residual 1064 nanometer, together with 532 to finally make 355 nanometer, the third harmonic. Sounds like science fiction, where such convenient magic crystals just happen to exist when they are needed. I wouldn't be convinced had I not enjoyed the outcome for the last couple of days. There are a few problems in the foundation of my story. Like, why is the beam bending here? How does anything get into beam dump 1? Can our precious UV yield really go back through the KTP? I hope somebody in the comments will clear those up without destabilizing my whole hypothesis. Anyway, we wanted to explore why impulse timing can change the transverse mode of the laser from something close to TEM00 to peanuts. Remember? It wasn't that long ago. There are many factors contributing to this, but we've got a big clue here. The laser's controller is pretty dumb. It never ever changes the pump diode current. It's around 6 ampere in standby and at any repetition rate and pulse width. We are constantly filling our neodymium-doped energy bucket at a constant rate. All that we can control is how often and for how long we pour out the bucket. That's also why we don't have a traditional power level setting in the software with this laser. We simply have to dump more often to get lower pulse energy. Unfortunately, changes in pulse power and energy also have consequences for the optics in the cavity we've just visited. All the crystals have losses, and those are not spread out uniformly in their volume. They get warmer where they are hit by a laser, and since their refractive indices are temperature dependent, they are practically causing heat-dependent distortions. That effect is called thermal lensing, and it can be counteracted, but not easily for the vast range of impulse energies that we can reach within the allowed range of bucket dumping frequencies. Here's some research where some mad lads have agreed to be shot in the eye with a laser powerful enough to see thermal lensing due to localized heating of their pre-retinal eye matter. Why? On that note, that's it for today. What a delightfully useful machine. I did not expect to like it so much. I thought my infrared MOPA would be all that I would ever need. And yeah, I probably still like that one a little bit better, but this was only my first contact with UV. So there's got to be more to discover, say photochemistry, laser plasma spectroscopy, or improved nanomachining through a microscope objective. Oh look, it still works. What a pleasant surprise. Thank you for watching. Very impressed once again with Commarker Omni 1. Get one before they are outlawed for your own safety.